In this problem set, we're going to be looking at various aspects of phase transitions and looking in fact at what we can learn about those molecules that are involved based on the material or the data that we get for those phase transitions. And in particular, we're interested in measuring non-ideality in these things. So in this first problem, we're going to do an interesting comparison. We're going to take the van der Waals equation of state, which represents a sort of a macroscopic description of a system. Macroscopic in the sense that we're dealing with bulk properties of matter. And we want to relate this to a potential, an intermolecular potential, I'll call it, which we call V of R here, which really is a microscopic set of information. And it's written in terms of a force for intermolecular attraction and a radius inside of which the two molecules can't get relative to one another. In other words, a hard sphere radius. The van der Waals equation of state is written in terms of the parameters A and B, and so what we're going to be doing in this problem is connecting these two sets of pieces of information. All right, what this means is that if you were to take this molecule and make some sort of macroscopic measurement on it and fit it to a van der Waals potential, you could then use that information to determine something about these parameters for the intermolecular potential. Now let me draw what this potential looks like. All right, we've got as a vertical axis our potential function, and as a horizontal axis we have the distance between two molecules. Now the first part here is telling us that when r is less than or equal to some distance, which we'll call sigma, the hard sphere radius, the potential is infinite, so it cannot go inside that wall. All right, when it is outside that radius, however, it's got this attractive potential that is governed by this parameter C6. So at r equals sigma, it'll have some value down here, and then it'll come up and rapidly approach zero as r gets larger and larger, because r is in the denominator here. So we have a potential that looks something like this. Now, admittedly, this is not the potential that you're used to. You're used to seeing something that looks more like that for potentials, but it's a close approximation to it. And by determining these parameters, if you know the van der Waals equation of state, it gives you some idea at least of what this potential looks like in reality. All right, we're actually going to go the other direction though. We're going to be given values for C6 and for sigma, and we're going to use those values to determine the van der Waals parameters based on these two formulas that were given here. And these are formulas that are reasonably straightforward to derive, although I'm not making you do that as part of this problem. All right, so in the first part, we are told that the hard sphere radius is given here. And what we want to do is find its value from the parameter b. Well, b is written in terms of that parameter, so it's a relatively straightforward matter. I do want to make a note, though. Be sure that you realize that 1 decimeter cubed is equal to 1 liter. Okay? And you'll need to make that conversion as you go through this, because you're going to need to report b in liters per mole. All right, so this should be fairly straightforward. You should be able to get a reasonable value for b based on the hard sphere radius. All right, now in the second part, we're going to do a similar analysis for a. And so we have another equation over here for a. Now notice that a depends upon this parameter C6. And we're not given C6. What we're given is what is the energy of the potential at its minimum. Okay, well look at this picture up here. Decide where the minimum of that potential is and how you might use that to get a value for C6, which you can then plug in. I also want to point out that these two expressions here are fairly similar. There are some aspects of them that look very similar. So you might be able to use your result for B from part A to help you find the parameter A in part B. Notice this interesting symmetry in this problem. All right, good luck with this one, and let me know if you have questions. We'll go on to problem 2 now. And in this case, we're looking at an analysis of a virial expansion, 2 different virial expansions, one in terms of pressure and one in terms of volume. So I'll remind you that the virial expansion looks like this. in the terms of pressure, it's going to be this plus higher order terms. And I'm purposely not writing out those higher order terms. I'm leaving it at this. All right, if I've got this as my y coordinate, actually z minus 1 is my y coordinate, and this as my x coordinate, what is that the equation of? All right, is it a parabola? You figure it out. But what you're given here is data that describes this function. And so what you'll want to do is to do some kind of numerical least squares analysis of this data to determine what value of b sub 2p would describe this data that you're given. Now I'll remind you that when you graph the compressibility, and I'll graph z minus 1 versus p, so p is our horizontal axis, we're going to start at 1 because this represents an ideal gas, it's 0 for z minus 1, and it's going to go down before it turns around and comes back up. This is the part of the curve that we are modeling with this. All right, so that should give you a big hint as to what kind of least squares analysis you should be doing. All right, in part B, we're going to do something similar, but for now, the other definition of the virial analysis, this one in terms of 1 over the molar volume, and again, there are higher order terms. This will be very similar to the first part of this problem, although I want you to note that we're given pressure and we're given a density in grams per liter. So what you'll need to do in analyzing this is you're going to need to be able to calculate the compressibility factor. So you'll need to look up what that is, how that is defined, and you'll need to convert this density into a molar volume. All right, you've got the atomic weight of O2. Actually, this is wrong. This is not the mass of O2. This is the mass of O. So you'll need to multiply this times 2 to get the mass of O2. Okay, be sure to do that. You'll need to then find this molar volume for each of these points as well as Z. Once you have Z, Z minus 1 and molar volume for each of these points, then you can do a similar least squares analysis to find the information that you need from this to solve for that second virial coefficient. All right, problem 3. Now we're going to use an equation that tells us how the heat capacity changes as a function of time. And this is in units of the gas constant R, so be sure you're aware of that. So in essence, Cp of T is going to be R times this expression that we're given here. All right, well, if we have the heat capacity as a function of temperature, that's going to allow us to find absolute entropy content, and it's also going to allow us to find a change in enthalpy, and that's the whole point of this problem. I'll remind you that the differential of entropy is simply the heat capacity at some temperature, dt, divided by T. So you'll need to go somehow from this to a delta S that will connect you to the value of the absolute entropy at 15K. All right, so we're giving you a little bit of a start here. We have the entropy value at 15K is what's given, and you'll need to go from this value of absolute entropy to the value of absolute entropy at, what are we given, 180K. So the delta S that you're going to compute is this one. And to that delta S, you will add the value of absolute entropy at 15K. All right, we're going to do something similar here for delta H, but remember that the differential of enthalpy is Cp of T dt. All right, so in each case, you're going to need to go from this differential expression to an expression for a delta, a change variable, change function of the variable, and that's what you're meant to compute in these problems. Problem 4 now, we're going to have a case of a vaporization of propane, and we're going to be looking at this in a couple of different ways. First of all, in part A, we're given delta vaporization of enthalpy and the delta vaporization of entropy. So I'll just remind you that the delta vaporization of the Gibbs energy at the point of vaporization is 0. So use that information and along with what you know about the Gibbs energy to determine TVAP. We've done this in a couple of practice problems, so it shouldn't be too difficult. All right, and the second part, though, is a little bit more challenging. And so I've added a hint here to help guide you in this. But let me just describe what the hint is getting at. What we have is propane in the liquid phase, and it is at a temperature of 250 K. And we want it to go to propane in the gas phase at 250 K. All right, and we want to know what is this delta H of vaporization. I will remind you, enthalpy is a state function. So however we can go from this condition to this condition, we should get the same value for the vaporization of enthalpy, delta vaporization of enthalpy. We know the vaporization of enthalpy when we're going along this path, when both of these things are at the vaporization temperature. Okay, that's what we have up here. We know this. So how can we connect these things to this? What is a path that will allow us to go from here to here and make use of this? Think about that. That's the whole essence of this problem, but I think once you figure it out, you'll see that the problem is actually fairly easy to solve. All right, in our last problem for this problem set, we're looking at isopropanol and its vaporization, and we're given the delta H of vaporization for this, and densities for its liquid and vapor states. Okay, so these are given here. This is for obviously for the liquid, and this is the density for the vapor. How do I know that? Well, liquids are a lot more dense than vapors. Okay, so that's what it is. All right, we're going to use the Clapeyron equation. So you need to look that up. It should be at the end of your problem set. But it's going to, actually what the Clapeyron equation is going to do is give you an expression for this differential. Okay, and it's going to be written in terms of quantities that you've got here. Notice, though, that it's also in terms of a quantity that is the change in molar volume for a phase transition. All right, well, you've got a phase transition going here, the phase transition from a liquid to a gas, and you've got information here about the densities, so you can use that to determine something about that. All right, so what you'll need to do is use the Clapeyron equation with the information that you've got here, and you should be able to come up with a value for this this slope. Now, notice the Clapeyron equation gives you this, and this is the one you're asked for. Well, I'll just say mathematically, you can always assume that this kind of relationship, well, I shouldn't say always, but in this particular case, you can assume that this particular relationship holds true. So that will give you a way to use that Clapeyron equation for that. All right, for part B, we're going to use this result to estimate the boiling point at a different pressure. Okay, remember these in these phase transitions, the temperature of the phase transition depends upon the overall pressure. So now we're raising the pressure to this. Presumably the normal one occurs at a pressure of 1 bar. And so that tells us, in essence, that we're looking at a change in pressure from 1 bar to 1.74 bars. And we will have a temperature of vaporization that's given here. And we want to know the new, so the thing we want is the new temperature vaporization, and we're going to subtract the old temperature vaporization. That's the delta T that corresponds to this. So delta T and delta P look a lot like a derivative done the old hard way. All right, so what I want you to do is to relate these things to the derivative that you got in the first part. It's not a difficult calculation. It just takes a little bit of thought to think about how you would organize this, but at the end of the day, it'll be a simple calculation. All right, good luck on this problem set, and please let me know if you have questions.